Good morning, everybody. Hope you're all well, rested. Exam tonight, I guess. Got to be excited about that. And maybe anxious excitement. The exam, as we said yesterday, you have a figures online that you can look at and refer to, and it's going to cover the quantum mechanics that we've done, so one-dimensional quantum mechanics and the quantum mechanics of the hydrogen atom and hydrogen-like atoms and building up the periodic table. And we'll talk about, there'll be some questions on Lewis structures and the accompanying accounting techniques, formal charges, oxidation numbers, and dipole moments, bond strengths, polarity, covalent versus ionic. Those are the basic topics that you should be familiar with, so you can look at your learning goals for those various things. And oops, if I could have the output of the tablet up on top. What we've been talking about today, and this is what we'll talk about today, we'll try to make relevant for the exam tonight, so remind you of the things that you might see on the exam tonight. We've been talking about polyatomic molecules and how do the wave functions that the electrons are inhabiting, so the standing waves about the nucleus, how are they modified when you start to talk about more than one nucleus? So if you have two nuclei and you want to have a box, a confined wave around two nuclei, then that changes the appearance of the standing waves. We said one way we could accomplish that is, well, just take one nucleus to start and say, well, the standing waves around that nucleus, the wave functions, the orbitals, all those are the same word, they all mean the same thing. How are those modified to accommodate approaching charges, approaching nuclei from other atoms? And the fundamental principle is we can add wave functions and sums and differences, what you call linear combinations. A linear combination is just adding things with constant coefficients. You can add and subtract the wave functions and produce new wave functions, and those are legitimate wave functions. So linear combinations of wave functions are still legitimate standing waves. They still solve the problem of that electron behaving like a wave confined to a box. Confined, it has boundaries, it's a wave, it will have standing wave patterns, it will be quantized. And remember, if you take nothing else home from Chem 1, take home the fact, quantization arises from boundaries placed on something that has wave properties. So the boundaries are going to be different when we talk about the molecules, but the atom itself, it can have creative wave functions, sums and products of the tradition, or sums and differences, linear combinations of the traditional s, p, and d orbitals that we've talked about. And that's important, and we should, just occurs to me that we should write a chem quiz or an exam question that kind of makes that obvious in the one-dimensional sense. So if you have the one-dimensional waves and you add them together, oh, we'll look at it. We'll look at it a bit here even today, maybe. Adding together the one-dimensional case and saying, oh yeah, if you add those two, you could come up with a sum of two wave functions, n equal 1 and n equal 2, and get a standing wave that also fits in the box. It's also a legitimate standing wave function. So that's what we did yesterday. We said we'll take the s and the p, one s and one p orbital, and we'll make two new wave functions. So an s and a p, you take the sum and the difference, two linear combinations, and you make two sp orbitals, 1, 2. This, what I'm drawing here, are just we know there's a out of phase portion for each of these wave functions. There's a node here in the middle where we have the plus and minus come together, but we have this is an sp orbital, and this is an sp orbital. So in general, I'm just writing the large in phase high amplitude part of the sp orbital, or the sp2 orbital. And the sp2 orbitals are here, and there are 3 of them. And we can do sp3 orbitals, and there'll be 4 of them from an s and 3 p's. And again, we're just writing the high amplitude part, and this smaller lower amplitude part kind of gets lost there in the picture. So that's what you're looking at. And importantly, we found when you add and subtract the wave functions appropriately, you do get orbitals that will accommodate the incoming nuclei to form bonds. So you get orbitals that have 120-degree bond angles or 109-degree bond angles. So you can use your existing atomic orbitals, hybridize them, this is called hybridization, to form orbitals that will accommodate the various steric numbers that you're going to encounter around a nucleus. So, I like to ask you about what is the energy level diagram. So how did the energy level diagram change? So here's carbon with 1s2, 2s2, 2p2. The valence electrons, 1, 2, 3, 4 valence electrons for carbon. You know that these are the electrons we're going to use for bonding. So they should occupy these new orbitals that we're forming, these sp type hybrid orbitals. How does that impact the energy level diagram? Well, we said when you make hybrid orbitals, you take an s and a p and you add and subtract them. You take the plus combination and the minus combination, and from these 2 orbitals, 1, 2, this is an s and a p, you're going to make 2 sp orbitals. So what I've done here is I've promoted that electron up here to the p, and now what I've done here is there's now at an intermediate energy between the s and the p. You'd imagine that's where the sum of the s and p come, the sp would land, and we're going to call that sp, and there's 2 of them, each having an electron in it ready to bond. So now I can fill this new atomic orbital diagram, and it looks like that. I have 2 orbitals that are atomic orbitals, and they look primed to make a bond. They have 1 electron in them. They're waiting for an electron from something else to come in and form a bond. They're waiting for another wave function to overlap. There's an electron there in a standing wave, and it's going to interact with the standing wave of an electron in the other atom that's coming in to form the bond. And you can just continue to do that. So that's the sp, and you could write that new electron configuration, the helium core, and 2, in this case, there are 2 sp orbitals, and the 2 sp orbitals have 2 electrons in them. And I do this just like the p's. I don't write out here px, py, pz. I know when I write 2p, I'm talking about a set of three orbitals. That's on the exam tonight. Well, you saw the picture already. There's a lot of stuff about that on the exam tonight, but I don't, when I'm writing the electron configuration, I don't write out all three. Same thing here. I know that there are two sp orbitals. This 2 doesn't mean there's two of them. This 2 is still n, the principal quantum number, okay? So 2 sp2, and you still have, actually, and I'm not going to say that either, but you still have the px and the py here, the 2p orbitals, and they will have an electron each. But in shorthand, I don't write that, I just put 2p2. We know when L is 1, p, those are the same thing, that we have 3 orbitals, one for each value of m sub L. And I can continue to do that. I can say, well, if I have to accommodate 3 things, then I need 3 bonding orbitals at 120 degrees from each other. So I'll combine another p, an SN2p, and I call that sp2. And now I have to be very careful. That's not 2 electrons. That's the name of the orbital, sp2. And there are 3 of them. So if I want to write that configuration, you can see now why I want those parentheses there. It's an sp2 orbital. And how many electrons do I have in those sp2s? 3, and 1 left in the remaining p. So you can see how the energy level diagrams work. The hybridization forms equivalent orbitals for bonding. Out of the existing s and p's, I form sps. And I can write them. Now if I write this electron configuration, this final one, 4 electrons, all spin parallel, 1 in each bonding orbital primed to make a bond, 1 in each hybrid orbital. Of course, now the p is not there at all. We've hybridized it into the sp3. Okay? So this is a beautiful summary of the Aufbau principle, filling up electrons from low energy to high energy. We have what we call the Hund's rule, and I don't call it that. We just say spins go in parallel to each other. They are spin parallel in equal energy orbitals. This is called degeneracy. Degenerate orbitals are orbitals that have the same energy. So the degeneracy of sp3s is 4. There are 4 equivalent orbitals along sp3. This is all the language you'll see on the exam tonight. So all this fits together. So let's do a chem quiz about that. Hybridization on the carbon orbitals in benzene. So these are the carbon. Oopsie. These are the carbons in benzene. As you know, C6H6. And how are those carbon orbitals hybridized? Which orbitals do the carbon atoms use to form that benzene structure? So let's talk about that among ourselves. TAs can find a group to talk with, and we'll see what you're thinking for that one. And I'll put up on overhead the suggestions if you need some suggestions to think about. If I could have the output of the lectern up top, you can talk about that. Okay, let's see what you're thinking about that one. I'm not sure I turned on the voting machine, but you can keep talking while I turn on the poll everywhere. And you guys can register your thoughts on that. Okay, let's see what your responses look like. SP2, incredibly popular. I agree with the SP2s. Why is that? You have to look at the carbon and say, what does the carbon have to accommodate? So it's highlight this carbon here. That's the one that we're interested in what it's doing. And it has to accommodate 1, 2, 3 things. And all the carbons are the same. All of the carbons have to accommodate 3 things. It just continues around the chain. Every carbon looks the same. Every carbon has to accommodate 3 things. How do I accommodate 3 things? Well, I need 3 atomic orbitals to do that. Well, what comes in sets of 3 at 120 degrees from each other? It's the sp2 orbitals. Don't be confused. It's not the sp3 that comes in groups of 3. sp3 comes from an s and 3 p's, so they come in groups of 4. We want an s and 2 p's to combine to form a set of 3 orbitals to accommodate the 3 things I have to bond with here. So sp2 is what we'd expect would happen. The steric number is 3. The bond angle is 120 degrees, and you can see that from the picture, but that is the description of an sp2. So the carbon hybridizes, it does this, and it has 1 p orbital left over that it didn't use. So there's a p orbital kind of coming out here at you and back into the, back behind the plane of the screen as well. So there's an unused p orbital that wasn't used to make those sp2 orbitals still on that carbon. Okay, that's cool. So now this carbon can bond to a hydrogen, and this carbon, and these carbons would also sp2 hybridize. So they would have orbitals at 120 degrees, and that will accommodate this carbon that has its orbitals at 120 degrees. And all of them have an extra unused p orbital that's coming out of the plane and then back behind the plane where you can't see it. There's this extra p unused, and there are the SPs, sp2s, that came from the s and the other 2 atomic p orbitals. Okay? That's the description of the bonding in benzene. So there you go. There's a description. This bond is an sp2 on one carbon to an sp2 on the other carbon. That bond is an sp2 on this carbon combined with an s orbital on that hydrogen. So you can see the wave functions, the s wave function and the sp2 wave functions, the description. Remember, when we say orbital, it's the description, it's the standing wave of the electron, and this standing wave electron has to interact with that standing wave electron, and that's going to form a bond between the constructive interference of this wave function and this wave function are what's going to form the bond between the carbon and the hydrogen. So here we are. We're in perfect conditions to talk about the multiple bonds, because we can have double bonds, but we're primed to see why that happens. So here is the carbon with the sp3 hybridization. So let's make it a little more obvious. So there's an sp2, I think I said sp3, sorry. sp2 orbital there, and then back here, that's an sp2. So there are 3 of those. This red and green is the leftover p orbital. And it has, of course, there aren't 2 of them. This is 1 p orbital. This is just the one lobe of the p orbital here, 1 lobe of the p orbital there. You would call that, if you label the axis, you would call that the pz orbital, if this is the z-axis. In general, we don't do that. In general, we let the z-axis be, it's just convention, it doesn't matter. But in general, we let the z-axis be the bonding axis. So this here would be the px that's left over, the py and the pz, and you can see that. I had to use the py and the pz because they are the orbitals in the zy plane. Those are the orbitals that you need in that direction. And the px is left over, standing outside like that. So here is going to be a chance for constructive interference between this standing wave and this standing wave electron. And that means there'll be high probability when these two add, they're in the same phase, they're going to add to form a standing wave, a new orbital, a molecular orbital that we call sigma, a sigma bonding orbital between those 2 carbons. Now we have to be a little careful because if we add 2 orbitals together, we have to conserve the number of orbitals. It's almost like conserving mass. The orbital represents the standing wave of an electron. So if you add orbitals together, you have to have the same number of orbitals at the end. So we take these 2 and we make 2 orbitals, a sigma bonding, and then something we'll call a sigma anti-bonding orbital. So we'll make 2 bonding orbitals, and we'll look at that, their energies in a minute here. But now just we're taking into account that we're conserving mass here. We're going to add an sp and an sp. We're going to form a sigma bonding and anti-bonding orbital to hold that together. And this bonding orbital will look like that. It will have electron density. Another way to look at it, of course, is all this green amplitude adds together, and this is the sigma bonding orbital that's the sum of 2 SPs. And then you can imagine you would subtract, do another linear combination, subtract the 2 SPs, and get the antibonding orbital. But we can see here, oh, look at this. These 2 orbitals now occupy the space above and below the plane. So here I can add and get constructive interference above the plane and constructive interference below the plane. So there I'm going to take the leftover PYs and add them to form a pi bonding orbital and a accompanying pi anti-bonding orbital. So you'll get the sum here above the plane, the constructive interference here, and below the plane as those 2 lobes of the p orbitals add together. And you'll have a pi bonding orbital. And that pi bonding orbital, you can see, has a node, a planar node right there on in the z-axis, the xz-axis plane, the xz plane. There's a planar node for that orbital. So that orbital has 1 node. The sigma orbital didn't have any nodes, so the pi orbital is a slightly higher energy. Nodes go like energy. If you have more nodes, you have a higher energy orbital. That's what you're going to see on the exam tonight, of course. And here it is now in molecular orbitals as opposed to atomic orbitals. Okay, so identifying nodes, understanding constructive and destructive interference, how to add wave functions, and you can see it was very important for that constructive and destructive interference that I remembered these have the same sign, they're the same color, so they're colors because that was the sign of the wave function in that region of space before I squared the wave function to get this probability distribution. So I remember that, and here you can see dramatically why we remember and use these colors to identify the nodes and to remind us, well, if these orbitals act like that, they'll be constructive interference. If this negative lobe were up here, then that would be destructive interference between the atoms. So there's the sigma bond formed from the sp orbitals, and I'll take two linear combinations, sp2 plus sp2 and sp2 minus sp2, to make a sigma bonding and sigma anti-bonding orbital. Two orbitals there. Here I'll form a sigma bonding orbital between the sp2 on the carbon and the s. No need for the hydrogen to hybridize. It can use its 1s orbital. It's the only one it has, and it needs that symmetric. Only has to accommodate one thing, one orbital, no need to hybridize. The s orbital on hydrogen, and you'll form a bonding orbital there and an anti-bonding orbital, the bonding orbital from one combination and the anti-bonding orbital from the other combination. And then the double bond is the pi bond, coming from adding and subtracting the py's on each carbon. So all of this now applied to molecular orbitals is a great review for your atomic orbitals that you're going to look at tonight on the exam. So now, what is the angle of this bond, knowing how hybridization and steric numbers and all that works? Can I determine this bond angle? So I've drawn the Lewis structure there to help you. So go ahead, let's talk about that amongst ourselves and see if we can come to a conclusion on that one. I will try to put up some suggestions for each answer there so you can talk about that. Okay. We'll turn on the voting machine there. Go ahead and register your thoughts if you have not yet done so. And, well, you couldn't have because I just turned it on. We'll see what you're thinking. Sorry, the microphone was not on. The electron has standing waves around it. Those standing waves that are D-type standing waves, S-type standing waves, and P-type standing waves, I add and subtract those together to form atomic orbitals that point at the vertices of a regular trigonal bipyramid. And I have hybrid orbitals that look like this, and there are 5 of them. Each one of these, remember, is a DSP3. That's a DSP3. That's a DSP3. There are 5 equivalent DSP3 orbitals. So, and we know, we've seen that example before, phosphorus pentachloride is something that does that, or iodine trifluoride. In that case, 2 of the orbitals would accommodate lone pairs rather than a bond. Steric number 6, I think you can imagine, you know the story. That's this. That's 6 equivalent orbitals, 2 Ds, an S, and 3 Ps are 6 atomic orbitals. They make 6 equivalent hybrid orbitals that have that orientation, and we know that that can accommodate sulfur hexafluoride or xenon tetrachloride with the 4 fluorines. And that's a square planar molecule. Beautiful. Okay, so this is good practice for today and the exam tonight. You know we love energy level diagrams. Which is the energy level diagram for phosphorus in PCl5, what we just saw on the previous slide? Let's talk about that among ourselves and see if we can come to a conclusion on this. If you get this, you really have followed the whole discussion, and maybe you've already done the reading. But this is a challenging, I think, chem quiz. So let's talk about it among ourselves. And I'll put some hints up on top. Okay, let's see what you're thinking. Excuse me, pardon me. So here's what you're thinking. A is quite popular. That's excellent. I agree with the A's. Let's talk through that together by ourselves. If I could have the panel back up on top. Oh, there's just all the information you might have used. So everything we've discussed so far. You have all these in your handout, so you don't need that. So here are the atomic orbitals. And you recognize this. S, 3s, the 3p, and the 3d. PCl5 has steric number 5. It needs to accommodate 5 things. How many atomic orbitals does it need? It needs 5 equivalent atomic orbitals. There are 5 equivalent atomic orbitals here, these d's. But they don't point in the right direction, do they? You've seen the d orbitals. They're all over the place. I can't accommodate a regular trigonal bipyramid. So I can't use them as they sit, but if I add and subtract them together cleverly, I can come up with a new combination that does. And we've just told you what that combination is. We've told you if you take, I need 5 things. Start from the bottom. I need 5 orbitals. I'll take the lowest 5 I can get to make my hybrids. S, P, 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 that gets me 4. And a d. That gets me 5 atomic orbitals that I can add and subtract in 5 linear combinations to get 5 new atomic orbitals. So after it's hybridized, there should be 5 equivalent orbitals somewhere. Unfortunately, A, B, and C all have 5 equivalent orbitals somewhere, so that doesn't distinguish it for you. So you have to look at the leftovers. You used your S, 3 of the P's, and 1 of the D's to make your SP, your DSP3 hybrid orbitals. So you took those 5 and you made DSP3s out of them. They point at the vertices of a regular trigonal bipyramid, but of course, the 3Ds, the 4 d orbitals that you didn't use are still there. So that's the energy level diagram that you would end up with. Okay? Brilliant stuff here. If you grasp all of that, you really understand the hybridization, this idea of linear combinations of your atomic orbitals make new atomic orbitals that accommodate the steric number that you're dealing with. Brilliant. We'll do that in discussion, I think. Well, actually, let's do this one now because it's good review for the exam tonight. So I'll just do this now. How do I describe the bonding in SEF4? First, write the Lewis dot structure, first step. And you would find, of course, I've left off all the dots around the fluorine. Fluorine has its octet as well, all of them, but I just lazily left those off. But you find that when doing that, that the selenium has 4 bonding pairs and 1 lone pair. That's a steric number of 5 there as well. And you'd say, well, steric number 5, I need 5 equivalent orbitals. That's my DSP3 orbitals I'd use to bond with. The VSEPR arrangement is trigonal bipyramid. That's where each of the DSP3 orbitals, how they're oriented. One of them contains a lone pair. So we put the lone pair there. You know, if you've been studying this, we make this seesaw configuration when we have 1 lone pair on a trigonal bipyramid. So the shape is seesaw, where the bond angles are around about 120 there and about 180 there. But we do know that they are compressed a little bit because there's this lone pair out there compressing those. and this one becomes less than. The bond is in fact less than 120, and this one's greater than 180 is the actual bonds. But I'm happy if you would have just got to 120 and 180 in that case, and then known, they're a little shorter than that, the deformation. Okay? So let's just keep doing this. Let's just keep adding the orbitals together. So far, we've just looked at the sums on the atom. Let's look at those sums that make the sigma and pi bonding and anti-bonding orbitals. So how do you describe covalent bonding? Well, let's go back to the very simplest case. If you have just the hydrogen molecule, H2, don't have to do any hybridization. All you have to do is take that wave function and that wave function and add them together, a 1s and a 1s, and you add them together, and you would get constructive interference if you take the sum, and that is lower energy than the 1s, the two 1s's separately. This is why bonding occurs. You can mathematically show bonding should occur because you can say, well, if I do take these wave functions, and I know they're very good approximations for what the electron is doing, if I take that mathematically and add those wave functions together and get this, and then calculate using the electron, essentially a fancy E equals z squared over n squared, to get the energy of this orbital, you'll find it's lower than the two individual s's. So indeed, bonding is favorable if you have the right number of electrons, and here we do, of course. So you take that, but you also do this, I said, anti-bonding thing. This is where you take the anti-combination, that's the sum, this is the difference, and then you would see, well, that, if those two add together, that would create a node in the middle, and that's bad for bonding. So we call that an anti-bonding orbital, but I'm required to do it because I have to keep track of all the electrons there. If I add two orbitals together, it's just conserving the number of electrons. I have to get two orbitals out. So now the two possible standing waves look like this, and I formed this anti-bonding thing, and it is higher energy, sigma star for anti-bonding, but it's okay because how do I do the bonds? Well, I had one electron in each of the 1s orbitals. This is the atomic electron configuration. And those would be paramagnetic. Oh my goodness, you have to do that on the exam tonight all over the place. I went a little crazy with the paramagnetism, sorry. Those are paramagnetic. They had an unpaired electron. Hydrogen, the molecule, so here are the molecular orbitals, is dimagnetic because those two electrons would end up down here in this bonding orbital. And now we see, oh, well, we had to form mathematically and physically to conserve wave functions, to conserve electrons. We had to form these two, but I can have my two electrons down in this orbital. They could be promoted to this. You could do an absorption and absorb a photon and promote them, but this forms a bond because that electronic configuration would be stable, lower energy than the two 1s's separately. But you can see what we'll do. We'll just continue doing that. What if it's helium? Well, helium would do the same thing. It's got 1s orbitals, so it would form a sigma and a sigma anti-bonding orbital to form the bond. But now I have 4 electrons, 2 from each helium, and you can see, well, then I would have to do this, have to put 2 of them there and 2 of them there. I'd have to use my rules for filling molecular orbitals, the same rules I would use for filling atomic orbitals, and I would say, oh, well, that's not going to work. He2 is not very favorable because you form this antibonding orbital as well. And indeed, that's what we find. Our molecular orbital theory, our quantum mechanical description explains why He2 isn't stable. It's not something you see. The He2, it helps us understand why that octet matters, why that duet on helium. Helium was already in a stable configuration because of its full quantum shell. Doesn't like to do bonding, antibonding orbital. And in true, if you do the math, it's not reflected here. If you do the math, the antibonding is, the energy you get is actually quite a bit higher. I drew them pretty symmetrically here, but it really is up here. So the sum of those is bad. It's much worse than the 2 1s's. So the mathematics would show you that's not going to happen. Again, keep going. Lithium. Now I would use the 2s orbitals. These would occur. I could do these 1s molecular orbitals, and then up here, the 2s could form a sigma and sigma star bonding and antibonding. And for lithium, you would predict, well, that has 2 electrons, so lithium, dilithium would be stable. You would predict that Be2, the molecule, wouldn't likely form. Bonding and antibonding electrons are canceling each other out, essentially. So we'll just talk through this one together. Which of the following diatomic species becomes more stable when you ionize it? This is brilliant. This helps us understand what we're doing tonight on the exam. We're talking about ionization. That's all over the exam as well. Ionization energies, well, hydrogen, helium, and lithium. The diatomics. Here they are. I've drawn the hydrogen, the helium, and the lithium. And the lithium's using 2s, so the lithium could have the 1s molecular orbitals, and you could start filling lithium all the way from the 1s molecular orbitals if you chose to do that. But it's just the highest energy that matter, the valence molecular orbitals, if that's what you want to call them, the highest energy molecular orbitals. So there are the configurations. Hydrogen would form 2 electrons in a bonding, 2 electrons in a bonding, 2 electrons antibonding, 2 electrons in a bonding. But I want to ionize them. What is that? Remove an electron. Not just promote it, but remove it from the molecule altogether. So the bond order is 1 here, it's 0 there, and 1 there. What is this thing called bond order? Well, just add up. So just bond order. Just add up the bonding electrons and subtract away the antibonding electrons, and you'll get the bond order. 2 minus 0 is 1. Oh, well, divided by 2 to get bonds. 2 bonding electrons minus 0, that's a bond. Every 2 electrons is a bond. That's bond order 1. 1, 2, minus 1, 2, bond order 0, and that's bond order 1. What about the ions? Well, if you ionize it, there I'm going to ionize the hydrogen. The bond order goes down by a factor of 1/2. That's half a bond. 1 electron in a bonding orbital, as you might guess. There's helium plus. I ionize that electron, and that's part of the exam material tonight, of course. You ionize the highest energy available electron, and when that's ionized, but here you've removed it from an anti-bonding orbital. So you actually make that He2 plus could form And you can do that in the gas phase. You can make He, the dimer, in the positive 1 state, and it does form a dimer. So again, quantum mechanics triumphs and predicts something that happens in nature, and lithium reduces in bond order just like the hydrogen in the ionic form. So you find that He2 plus, the bond order increases. Oh, let's do our check-in. Are you ready? Everybody logged in, ready to go? You should see that in front of you. Oh, and it's actually unlocked. There, it's locked. I'm going to unlock it again. Okay, everybody, happy with that? Okay, we'll continue on. Now we can describe that pi bonding. The pz orbitals can overlap. Now here it was important that we call this the z-axis. And we often say that the internuclear axis, the axis that contains the nuclei, is the z-axis. That's just convention. You could be any axis. So that means two pz orbitals could overlap, and they would form a sigma bonding and sigma antibonding orbital. In this case, the plus combination is antibonding because, here we go again, we have to know this. This and this give you destructive interference. Those destructively interfere if you reverse this one, that is, take the minus combination, then you would have constructive interference, two of the same color lobes, and you would form that. Now, the px and py are left over, and they are above and below the plane, so the pyx here and the py coming out at you, but they are equivalent in energy, and you would add 1, 2, 3, 4 atomic orbitals, and you would form 4 molecular orbitals, the pi bonding and then pi antibonding when you add them with the opposite sign. And you would do that. Well, I get take 4 atomic orbitals, I make 4 molecular orbitals, and then I can do the same thing. I can fill them with the available valence electrons that were in these orbitals to begin with. So here that is summarized. So boron, B2, it starts filling. Now I've left out the orbitals below this. So 1s sigma star. And I've even left out here the 2s and the 2s. I'm looking at just the p orbital. Oh no, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. I'm using the sigma from the p's and the 2 pi orbitals from the p's. So this is the p orbital bonding, and boron, you have 2 electrons in the p orbitals to come in. Carbon, you know, 2p electrons from each carbon would go 4, and you can see they fill. You don't go up to here yet because you can pair, use your the principles you know to fill orbital diagrams. And what we have here is just this is just a molecular orbital energy diagram. We did it for atomic orbitals. Now we're just looking at the molecular orbitals formed from the atomic orbitals, but you fill them the same way. Now, you'll notice one thing here, and you don't have to know it. Important. You notice how boron, carbon, and nitrogen, the pi bonding orbital is lower in energy than the sigma bonding orbital? That you don't have to know. It is, that's just the math. So whenever you need one of these orbital energy level diagrams, I'm going to give it to you. So you don't have to remember what the order is. I will give it to you so you get the ordering. Because I want you to be able to fill them and predict something about the molecule, but I don't care if you don't remember this particular detail, that before nitrogen, the pi are lower, and then oxygen on, the sigma bonding is a little lower. I don't care if you know that or not. By the time you get here, it's all full anyway, so it doesn't really matter, but I will draw the energy level diagrams for you. And you can see, here for oxygen, I take the p electrons for oxygen, 1, 2, 3, 4, 5, 6, 7, 8, from 2 oxygens, and I would put them in the p sigma bonding orbitals and the p pi bonding orbitals formed from the p orbitals on the atoms, and fill them on up, adding 2 electrons as you go. Okay? So Karen can show us something brilliant here. Here, we've talked about this for an hour now, and we get to another of the great triumphs of the quantum mechanical description of molecules as opposed to the Lewis dot structure. If I write the Lewis dot structure of oxygen, and nitrogen, is there anything about either of those that would tell you if it was paramagnetic or a diamagnetic? If you looked at it, you would guess diamagnetic. It looks like everything's paired, doesn't it? But look at this. If you look at the molecular orbital diagram, molecular oxygen is paramagnetic. Molecular nitrogen is not. Okay? So, Karen, and remember I told you, and you guys were incredulous. You didn't believe me. You said, I said, if it's paramagnetic, it will literally be attracted to a magnet, the atom itself. And you said, no way. And I say, way. Karen can demonstrate it. What does she have here? She has a giant magnet. Are you going to get a camera 4? She has a giant magnet, and here she has liquid nitrogen and liquid oxygen. So she has a supply of those molecules. Do we have them up top? And look at how beautiful liquid oxygen is. This beautiful pale blue color. So it's got a pale blue color. What is liquid oxygen doing? How is it interacting with visible light? Yes? It's absorbing some of it. It's blue. Liquid oxygen is absorbing somehow some visible light. What kind of wavelengths? Oh my God. Lower, yes, because I'm seeing, lower energy. I'm seeing the higher energy. So I'm absorbing the long wavelength, the low energy, low frequency reds, and I'm seeing the blues. Okay? Freaking gorgeous. So Karen, demonstrate this to us. You can take liquid nitrogen, and our assumption is liquid nitrogen is diamagnetic. It shouldn't interact with a magnet. And she pours that over. That's good. You don't have to get too much closer there on the, I don't think, on the camera shot. That's beautiful. Get a focus there. Nitrogen pours right on through the poles of that permanent magnet. Not attracted. And you would say, well, how do I even know that's a magnet at all? Don't come near it with metal. You'll find out in a hurry. But look at this. We'll pour liquid oxygen over the poles of that magnet. Holy mackerel. Look at that. Liquid oxygen suspended between the poles of the magnet. Each individual molecule held in that magnetic field because of its paramagnetism. That is a gorgeous display of the triumphs of quantum mechanics. Lewis dot structures don't cut it. Lewis dot structures don't tell us that. But our molecular orbital description of oxygen does predict that. That is fabulous. Yeah, do it again. That's how cool that is. Liquid oxygen suspended between the poles of a magnet. And Karen's walked away, so don't go near it, don't disturb it. Let's just see, look at that, right at the end, the gas. Oh, so freaking cool. The gas molecules suspended between the poles of the magnet. Okay. The formation of O2 molecules from O2 atoms, how does the total paramagnetism of the sample change? So this is a beautiful one. Why don't we talk about this one, because you have to, this is a question you could almost get, half of this question you could get on the exam tonight, because, and you do. You have to talk about atomic paramagnetism. Molecular paramagnetism won't be on the exam, of course, but half of this question is on the exam tonight. So let's talk about it amongst ourselves and see if we can come to a conclusion on that. Okay, brilliant. Let's allow you to register your thoughts on that one. Louise. I'm so sorry about those watching remotely. I keep forgetting to turn my microphone back on. Sorry about that. There are 6 molecular orbitals coming from 3 p orbitals on each oxygen. And you can fill those. I have 1, 2, 3, 4. 1, 2, 3, 4. I have 4 electrons here, 4 electrons here. So I have to get 8 into here. And 1, 2, 3, 4, 5, 6, 7, 8. I have 2 unpaired electrons there. So the paramagnetism of the sample decreases. 2 oxygens have a total magnetism of 4, and the oxygen molecule has just 2. Okay? All fantastic stuff for both the exam and understanding what we're talking about today. Okay, we'll talk about this one together. Consider the ionization and electron capture in N2. Also good exam material. Here we're talking about ionization, losing an electron, or electron capture. This is the electron affinity of the nitrogen molecule, which is true about the relative bond strengths or bond orders. Bond order is the same as bond strength. The higher the bond order, the higher the bond strength, the stronger the bond. So here is N2. And remember, like I said, this I would give you. You don't have to come up with the molecular orbitals for nitrogen, the molecule. You could probably label them. You know these are pi's because they come in a set of 2. That's a sigma. This is a pi star. It's the anti-bonding combination of that. And this is the sigma star. I wouldn't have any trouble asking you to label them if I give you the order because you know how they're constructed. So that's something you could do. But the ordering you would get on the exam. And then it's easy to calculate the bond order. In fact, essentially you have to do that. You have to know that's bonding, and this is anti-bonding, and this is anti-bonding to do that because you have to recognize these are bonding electrons and these are anti-bonding electrons. So here I have 1, 2, 3, 4, 5, 6 bonding electrons, no anti-bonding electrons. So 6 electrons can make 3 bonds, and we're super happy about that because we know that agrees at least with our electron dot structure. If we drew the electron dot structure, we did say triple bond to nitrogen. So that's nice that we see that reflected in the molecular orbital theory. Nitrogen minus, adding electron, goes into an anti-bonding orbital. That weakens the bond because that's an anti-bonding orbital. And of course, subtracting an electron, ionizing, takes an electron out of a bonding orbital, also weakening the bond. So we see that the bond order of the electron capture and the ionization both weaken the bond. Oh, I love this. Oh, let's put this on the exam. Not yet. Why is this so cool? What picture could I draw about the relative stability of these two things? What would be at the bottom of the well? The energy of N2, that bond energy, and up here is N2 plus and N2 minus. Look at that. This is why N2, we would say, is stable, because going anywhere else is uphill in energy. What a beautiful way to summarize everything that we've talked about in class. We'll see you, we won't see you physically, but good luck tonight. And we'll see you tomorrow morning. Oh, two things. Tomorrow morning, of course, we have the bonus question you do by poll everywhere. Thursday, we have the pop quiz. And I'll remind you tomorrow, but let's do this. It would be fun to take a class picture, I think. For me, I don't know if you guys would care. But Thursday, I'll post an announcement. Wear something, if you want, wear something blue and gold. Wear some Cal apparel, and then we'll get down here and take a group picture. That's optional, but I think it'll be fun. You'll do a favor to me. Group picture Thursday. I'll post an announcement after the pop quiz.